All right, so in this talk, I'm looking at how chemically distinct regions in the mantle can survive um, despite convection in the mantle, trying to stir these regions up and mix them in with the rest of the mantle. And in particular, what I'm looking at is there's known to be chemically distinct regions that form very early on in Earth's history, almost as soon as the planet forms, so 4 to 4.5 billion years ago. And the signature of these regions lasts and is seen in rocks for the next about 1 billion years. So rocks that are as old as 3 to 3.5 billion years that have been looked at in Canada and Greenland still show some of this distinct chemical signature. And it's very surprising that that signature would last for so long, for about 1 billion years, because in the past, when the mantle was much hotter, it was convecting and fluid motions were supposed to be much faster, and that should mix this chemically distinct region up and erase it fairly quickly. So much you would expect it to not last 1 billion years. But what I've done is point out that there's another important effect happening, which is that grain size in the mantle has an important influence on how fast it can move. And when temperatures are hotter, which normally makes fluids like syrup or honey flow faster, it also makes grains grow faster. And larger grains actually slow down the flow of rocks and the flow of tectonic plates at the surface. So if you take this grain size effect into account and do some new simulations like I've done, what we found is that indeed you can get chemically distinct regions to survive in the mantle for 1 to 2 billion years, just like the geochemical observations show.